August 1943. A damaged American P-47 Thunderbolt makes an emergency landing in occupied France. For the Luftwaffe and the Reich's Technical Intelligence Division, the capture of this nearly intact aircraft is a windfall. For months, German fighter pilots had reported encounters with this new, overweight American machine that seemed to defy logic, a monster that climbed faster, dove harder, and survived punishment that should have torn any aircraft apart. Now, for the first time, engineers could study the mystery up close. On the dusty runway of a small Luftwaffe airfield, technicians gathered around the silver-gray machine whose wings bore bullet holes, yet whose structure remained astonishingly sound. The first impression was disbelief. The P-47 looked grotesque by German standards, a massive radial engine brute twice the size of a Messerschmitt or Focke-Wulf. Its bulk contradicted every principle of German design philosophy, which prized aerodynamic elegance and minimal weight. But what seemed at first a clumsy giant would soon reveal a truth far more unsettling. It was a symbol of industrial power. Germany could not hope to match. When engineers removed the cowling, the source of that power stood before them, the Pratt & Whitney R2800 double wasp engine. 18 cylinders, arranged in 2 rows of 9, capable of producing 2,000 horsepower. It was not merely powerful, it was a masterpiece of precision manufacturing. Each component was machined to tolerances that wartime German factories could rarely achieve. No shortcuts, no signs of metal scarcity, no simplification for mass production. Every piece reflected abundance. The Americans were building machines as if resources were infinite. What shocked the engineers even more was the integrated turbo supercharger system, through a labyrinth of ducts and turbines. Exhaust gases drove a compressor at 20,000 revolutions per minute, maintaining power even in the thin air above 25,000 feet. Germany had experimented with turbo systems but never managed to field them successfully. The metallurgy and heat-resistant alloys required were beyond reach. Yet here it was, fully operational, installed in a production fighter built by the hundreds each month. The technical gulf was undeniable. The P-47 was built around reliability, redundancy, and ease of maintenance. Each cylinder could be removed and replaced individually. Backup systems ensured continued operation even after severe damage. In contrast, German engines demanded complete disassembly for the smallest repairs. To the engineers examining the Thunderbolt, it was as if the Americans had designed for a different kind of war, a war of endurance and logistics, not perfection. Then came the numbers. The reports from occupied Europe and Allied intelligence indicated that American factories were producing P-47s at a rate of 500 per month. The same engine powered multiple aircraft types. Over 125,000 R2800 engines were projected for production. German factories, strained by shortages, could not produce even a fraction of that capacity. For the first time, the engineers confronting this machine began to understand that the outcome of the war would not be decided solely in the skies, but in the factories behind them. Every detail of the Thunderbolt told the same story, from the thick aluminum skin that absorbed cannon fire to the redundant control lines shielded within its structure. It was over-engineered, overbuilt, and overwhelming in its durability. Where a Bf-109 sacrificed armor for speed, the P-47 embraced mass as protection. Where German fighters relied on agility, this machine relied on power. Its philosophy was industrial, not artisanal. By the time the examination ended, the conclusion was unavoidable. This was not simply a fighter aircraft. It was a statement of national capability, a machine produced by an economy so vast that it could afford precision where others cut corners, power where others conserved fuel, and standardization where others struggled with scarcity. Germany engineers left the airfield that day with a silent understanding. They had just looked at the future of industrial warfare, and it did not belong to them. The P-47 Thunderbolt stood as a mechanical prophecy, one that revealed a truth few dared to speak aloud. Germany was not losing because of inferior pilots or tactics, but because it was fighting an enemy whose factories, resources, and engineering philosophy had already decided the war before the first dogfight began. To understand why the P-47 Thunderbolt changed the war, One must begin with its beating heart. The Pratt & Whitney R280 O double wasp, 18 cylinders of forged steel and aluminum, arranged in two concentric rings, each one firing in perfect rhythm. It produced 2,000 horsepower, and yet the power itself was only half the story. What truly mattered was how it was built, and what that construction revealed about the industrial mindset of the United States at war. The double wasp was not designed in isolation. It was born from an ecosystem, thousands of subcontractors, machine shops, foundries, and test facilities synchronized across the American continent. The engine's reliability was not a miracle of genius, but a triumph of systemization. Each component could be built in a different city, shipped by rail, assembled on a production line, and fit perfectly with every other part because every bolt, thread, and tolerance adhered to exact standards. This was the power of American industrial discipline, mass precision. German engineers, trained in a tradition of craftsmanship and custom fitting, could not replicate that scale. In Germany, the finest aircraft engines, like the Daimler-Benz DB605 or the BMW 801, were masterpieces. But each was almost handcrafted, adjusted manually to meet tolerances, consuming time and skilled labor. In America, machines built machines. Gauges, jigs, and automated lathes produced identical results hour after hour, shift after shift. The double wasp was designed for that world, modular, durable, repeatable. Its internal components reflected abundance. The crankshaft, a single piece of high-tensile steel, was polished to mirror finish. Bearings were made from alloys containing nickel, chromium, and molybdenum, materials that Germany by 1943 could only dream of obtaining in sufficient quantity. The Americans weren't constrained by scarcity. They were empowered by supply. Industrial chemistry had become strategy. At its core, the double wasp was a paradox. It was simple enough to maintain under combat conditions, yet complex enough to perform flawlessly at high altitude. Its air-cooled design meant it could take punishment that would destroy a liquid-cooled German engine. Bullets that severed a coolant line in a Bf-109 or Fw-190 meant instant failure. A P-47 hit in the cylinders could keep running on sheer mechanical resilience. American engineers had accepted inefficiency in favor of endurance, and it worked. But the most revolutionary aspect was invisible from the outside. The turbo supercharger, a labyrinth of ducts, carried hot exhaust gases to a turbine in the tail of the aircraft, which spun at over 20,000 revolutions per minute. The turbine compressed air and forced it back into the engine, maintaining sea-level power even in the stratosphere. This was engineering elegance through brute force, the mechanical equivalent of bending physics to human will. The turbo supercharger system required advanced metallurgy. The turbine blades had to endure temperatures exceeding 700 degrees Celsius without warping or failing. German manufacturers simply didn't have the alloys or precision tooling to produce such parts consistently. The United States did not because of one inventor, but because its factories were capable of producing millions of components to identical specifications. The double wasp was more than an engine. It was proof of an industrial civilization's maturity. By late 1943, Pratt & Whitney was producing over 2,000 R2800 engines per month. These engines didn't just power the P-47. They drove the F-6F Hellcat, the F-4U Corsair, the A-26 Invader, and even twin-engine bombers like the B-26 Marauder across the U.S. Army, Air Forces, Navy, and Marine Corps. One engine type powered an entire generation of aircraft, something no other nation achieved. Standardization was not a compromise. It was efficiency turned into dominance. In contrast, the Luftwaffe fielded a dozen different engine families: Daimler-Benz, Junkers, BMW, Argus, each with its own supply chain, tooling, and spare parts. What for Germany was diversity, for the Americans was unity. The result was logistical strength. Maintenance crews in the Pacific or Europe could replace parts, swap engines, and train mechanics with identical procedures. Every pilot who climbed into a P-47, Corsair, or Hellcat carried with him the same heartbeat of American industry. The double wasp's performance transformed strategy. It allowed American fighters to escort bombers deep into enemy territory, climb above 30,000 feet, dive faster than anything in the sky, and survive hits that would cripple any rival. German pilots who called the Thunderbolt the flying tank weren't exaggerating. Beneath its armor was an engine that refused to die. In 1944, Luftwaffe intelligence compiled reports from recovered wreckage. One engineer wrote bluntly, "The Americans are building engines that cannot be destroyed faster than we can build those that fail." It was not hyperbole. By 1944, Allied aircraft production exceeded Axis output by more than 3 to 1. The R-2800 alone existed in over 125,000 units, more than the total number of all German aircraft engines of equivalent class built during the war. What the German analysts understood, and their leaders refused to accept, was that the war had shifted from a contest of courage to a contest of capacity. The R-2800 embodied that truth. Its every bolt spoke of foundries, machine tools, and workers across an entire continent mobilized toward a single purpose. When the P-47 thundered through the European sky, it carried not only a pilot and ammunition, it carried the weight of an industrial civilization that believed in abundance, standardization, and problem-solving through scale. The Germans called it over-engineered. The Americans called it dependable. History would call it decisive. By the spring of 1943, the P-47 Thunderbolt had moved from prototype to the front line of war. What began as an engineering marvel was now tested in the crucible of air combat. Over the skies of Europe, North Africa, and later the Pacific, the aircraft that German engineers had once mocked as a flying milk bottle would prove to be one of the most devastating weapons of the Allied arsenal. When the 56th Fighter Group received its first P-47s in England, pilots were skeptical. It was heavy, slow to climb, and enormous compared to the sleek Spitfires beside it. But as missions extended deeper into occupied Europe, the true purpose of the machine became clear. At high altitude, where Luftwaffe fighters began to lose power, the Thunderbolt came alive. Its turbo-supercharged engine delivered full horsepower where German aircraft gasped for oxygen. In the stratosphere, above 25,000 feet, the P-47 could dive faster than anything in the sky and recover. Its first real trial came in April 1943 during bomber escort missions over the Netherlands. Luftwaffe pilots, confident in their Messerschmitt Bf-19s and Focke-Wulf FW-190s, expected an easy kill. What they encountered instead was a machine that absorbed cannon fire, retaliated with 8 50 caliber guns, and climbed away trailing smoke, only to return moments later. German intelligence reports from the time began to reflect disbelief. Enemy fighter continues to fly despite numerous hits. Unlike the delicate German designs optimized for agility, the P-47 was built to survive damage and return home. Pilots often landed with entire cylinders shot out, oil leaking across the canopy, wings shredded by flak, yet the aircraft remained controllable. In one recorded case, a Thunderbolt returned to base with more than 200 bullet holes and part of a wing missing. It was repaired, refueled, and flying again within days. The Thunderbolt's strength was not elegance, but endurance. Each mission demonstrated that survival was as decisive as speed. American pilots learned to dive, strike, and climb back to altitude, a hit-and-run style of air warfare that played directly to the P-47's strengths. The Luftwaffe, accustomed to short, agile duels, found themselves facing an opponent they could neither outrun nor outlast. As Allied bombing campaigns intensified, the P-47's role expanded from escort to offensive air superiority. Thunderbolts escorted B-17s and B-24s deep into enemy territory, tearing through interceptors that tried to reach the bomber formations. Their 50 caliber guns shredded enemy aircraft with overwhelming firepower, 8 barrels firing 100 rounds per second. What they lacked in cannon shells, they compensated for in sheer volume and ballistic energy. On the ground, the Thunderbolt became equally feared. Its ability to dive at near supersonic speed made it one of the most effective fighter bombers of the war. In Italy and France, and later during the invasion of Normandy, squadrons of P-47s devastated supply convoys, rail lines, and armored divisions. Its rugged airframe allowed it to dive steeply, release bombs, and pull out under intense flak where lighter aircraft would have disintegrated. For German troops, the roar of a P-47 engine became a warning of annihilation. Soldiers described the sound as a metallic thunder. The origin of the aircraft's name? From 10,000 feet, the Thunderbolt's 8 machine guns could rake a column of trucks or tanks with terrifying precision. It could deliver rockets, bombs, and gunfire in a single pass and still have the strength to climb back to altitude. The Luftwaffe, stretched thin and outnumbered, could do little to stop them. In the summer of 1944, as Allied forces advanced through France, the Thunderbolt became the aerial backbone of Operation Cobra, the breakout from Normandy. In a single day, P-47s flew over 1,200 sorties, obliterating German armored concentrations. The Luftwaffe barely appeared. Its fuel was running out, its pilots exhausted, its aircraft inferior. In reports from the field, German officers wrote that the American fighter bombers make movement by day impossible. The statistics told the story. In the European theater alone, P-47 pilots destroyed more than 7,000 enemy aircraft to 3,752 in aerial combat and another 3,315 on the ground. They also destroyed over 86,000 railway cars, 9,000 locomotives, and 6,000 armored vehicles. The Thunderbolt had become not just a fighter, but a symbol of total air dominance, a mechanical avalanche rolling over a nation that had once ruled the skies. For American engineers, every returning aircraft was data. They analyzed battle damage, studied failures, and modified production lines accordingly. Each improvement reached the front faster than the enemy could adapt. New propellers, improved gun sights, reinforced wings, all were added without halting mass production. In a sense, every Thunderbolt in combat was both a weapon and a prototype for the next one. By 1944, German pilots facing the Thunderbolt knew what it meant. They were fighting the industrial power of an entire continent. No amount of skill or bravery could compensate for the numbers, the machinery, and the relentless innovation that the P-47 represented. The skies over Europe had become a demonstration of industrial mathematics, the equation of quantity multiplied by quality. Every time a P-47 returned home riddled with bullets but intact, the message was clear. America had built not just an aircraft, but a system that could not be broken. By 1944, the air war over Europe had become more than a clash of pilots. It was a collision of economies. Every dogfight between a P-47 and a Messerschmitt represented something larger. To civilizations waging war through metal, machines, and manpower, the Americans had not simply outdesigned their enemies, they had outbuilt them. The P-47 Thunderbolt stood as the perfect embodiment of that industrial philosophy. Behind every aircraft lay an invisible network. Miners in Pennsylvania extracting bauxite, foundries in Detroit melting aluminum, and thousands of assembly workers from Kansas to Connecticut tightening bolts in synchrony. Each Thunderbolt that rolled off the production line was the product of 20,000 parts, 400 subcontractors, and a nation whose economy had become a weapon. In 1939, the United States produced fewer than 3,000 aircraft per year. America's industrial system was built for mass replication. The same precision that produced millions of cars before the war now produced millions of parts for fighters, bombers, and transports. The United States had mastered interchangeable manufacturing, a principle Germany never fully adopted. In Germany, shortages and decentralization forced factories to produce components by hand. No two aircraft were perfectly identical. Repairs required fitting and refitting. Each fighter was unique, and that uniqueness, once a source of pride, became a fatal inefficiency. The Luftwaffe entered 1944 already at a disadvantage. Strategic bombing crippled fuel plants and engine production. Allied blockades cut off access to rare metals like chromium and tungsten. Skilled machinists were drafted or killed, replaced by forced laborers with minimal training. Meanwhile, across the Atlantic, the U.S. War Production Board ensured a steady flow of steel, copper, and fuel. There was no improvisation, only expansion. The results were mathematical. In a single month, American factories could produce more aircraft engines than Germany could in half a year. While German pilots rationed flight hours to conserve fuel, American trainees logged hundreds of hours before combat. By the time they reached the front, they had already flown more than many veteran Luftwaffe pilots would during the entire war. In the skies, that imbalance translated into momentum. The P-47, once doubted for its bulk, became a symbol of unstoppable force. Each destroyed Thunderbolt could be replaced within days. Each improvement in design could be implemented within weeks. Germany, bound by bureaucracy and scarcity, could not react fast enough. Even its most advanced creations, the Me-262 jet fighter and the Tu-152 high-altitude interceptor, arrived too late, produced in numbers too small to change the outcome. In Berlin, intelligence officers began to notice the pattern. Reports from captured factories and intercepted communications all pointed to the same conclusion. The United States was not fighting one war. It was fighting 10 and winning all of them at once. Tanks, ships, bombers, and fighters poured from its factories faster than the Axis could destroy them. A secret report to the German Armaments Ministry in late 1944 summarized the reality with chilling precision. The American war machine functions as a single organism. Losses do not weaken it. They stimulate production. Every destroyed plane generates 2 replacements. That statement was not rhetoric. It was data. Between 1943 and 1945, American aircraft losses exceeded 40,000, yet total numbers at the front increased every month. The system was self-sustaining. War had become industrial rhythm. An assembly line extended into the sky. When the P-47 flew missions over France or Germany, its presence was not only tactical, it was symbolic. Each sortie was proof that the United States could project power indefinitely, that its strength came not from the genius of a single man, but from the collective precision of millions. In the ruins of German factories, engineers could see the contrast. Where they worked with scarcity, the Americans worked with abundance. Where they relied on improvisation, the Americans relied on systems. And where they worshipped perfection, the Americans embraced practicality. The war had shifted from art to arithmetic, and arithmetic was merciless. By the beginning of 1945, it was clear that Germany could no longer replace what it lost. Aircraft were grounded for lack of fuel. Engines failed for lack of metals. Pilots died faster than they could be trained. Meanwhile, the Thunderbolt kept flying, heavier, louder, but indestructible. The war of the skies had become the war of factories. The winning side was not the one with the most daring pilots or the most advanced technology, but the one that could build faster, repair faster, and adapt faster. And in that war, the P-47 was not just a fighter, it was the physical manifestation of a nation's industrial soul. It began not with explosions, but with silence. In August 1943, at a Luftwaffe testing ground in occupied France, German engineers surrounded a captured American fighter that had made an emergency landing. The aircraft was almost intact, its pilot captured, its engine still warm. It was a P-47 Thunderbolt. To the men inspecting it, the discovery was meant to be a victory, proof that they could learn from the enemy. But as the examination continued, the mood in the hangar shifted from curiosity to unease. What they found inside the machine did not reveal weakness. It revealed something far worse, a civilization that had mastered the science of mass perfection. The lead engineer, Oberleutnant Werner Schultz, recorded his impressions in a report later archived by Allied intelligence after the war. He described the aircraft as grotesque in form, but perfect in function. He noted the R-2800 engine's staggering horsepower, the machining precision of its components, and the immaculate finish of its internal systems, untouched by shortages or corrosion. It is the work of a nation that has never known scarcity, he wrote. Schultz and his colleagues had been trained to believe in German superiority of design, of intellect, of craftsmanship. Yet every rivet of the P-47 contradicted that faith. The Americans had achieved something new. Engineering as an industry rather than an art. The Thunderbolt was not handcrafted brilliance. It was calculated efficiency. When Schultz examined the turbo supercharger, the reality struck him harder than any bomb. The system was far beyond what Germany could replicate. The metallurgy required heat-resistant alloys, precision bearings, temperature-tolerant ducting demanded a manufacturing base capable of producing thousands of identical parts. Germany could produce prototypes. America could produce thousands. One of his assistants, a mechanic from Bremen, reportedly said in disbelief, "Herr Oberleutnant, this aircraft is not built to win battles. It is built to win wars." That was the truth they all understood, but could not say aloud. Every component of the P-47, the vast engine, the redundant controls, the modular armor, was not just a piece of technology. It was a statement of national capacity. And for the first time, German engineers realized that capacity was what they lacked. When Schultz compared the numbers, the truth became unbearable. The United States was building more than 500 P-47s per month, more than Germany could produce of all fighter types combined. The same engine that powered the Thunderbolt also powered other American aircraft, Corsairs, Hellcats, Marauders, in quantities that defied comprehension. It was not a contest of design anymore. It was a contest of replication. In internal memos, some engineers dared to voice their despair. "We cannot win an industrial war," one wrote anonymously to Albert Speer's office. "They can lose aircraft faster than we can build them. They can afford inefficiency. We cannot." But such realism was dangerous. Within the Reich, to speak of inevitable defeat was to invite suspicion of treason. Schultz's report, precise, technical, and emotionless, was dismissed as pessimistic and defeatist. His warning vanished into archives marked "no action required." Behind closed doors, however, the shock spread. Officers of the Luftwaffe's technical branch began quietly lowering their expectations. They no longer discussed matching American production. They discussed delay and defeat. Engineers spoke in whispers about materials they could no longer obtain, factories that no longer delivered, and systems they could not repair. The collapse was not only material, it was psychological. Men trained to believe in the perfection of German science now realized they had been overtaken by an industrial civilization that valued imperfection if it meant scale. The Americans did not build the best machine. They built enough of them to make perfection irrelevant. Schultz would later recall in his post-war interrogation that the most terrifying moment of his career was not hearing Allied bombers overhead, but standing beneath the P-47's enormous engine and realizing that his country could never produce its equal. "I knew then," he said, "that the war was already lost." His conclusion was not unique. Similar sentiments appeared in the diaries of captured officers and engineers after. 1944. One Luftwaffe colonel wrote, "We have reached the limits of German ingenuity. The enemy has reached the limits of human organization. The P-47 became more than an airplane. It became a mirror reflecting the truth that ideology had denied. It showed that courage without capacity, innovation without resources, and pride without production could not sustain a modern war." And as the Allied bombers filled the skies over Germany, escorted by endless waves of Thunderbolts, the engineers who had once built the Reich's air fleet watched their own factories burn, knowing that even if they could rebuild them, they would never match the system that produced the machine before them. For the men of the Luftwaffe's technical corps, the war ended long before the surrender at Reims or Berlin. It ended in that hangar, under the shadow of a captured American aircraft that embodied the one thing the Reich could never produce: abundance. By early 1944, the skies over Europe were no longer a battlefield. They were a calculation. Every morning, Allied controllers launched hundreds of bombers and escort fighters from England in clockwork rhythm. Every evening, fewer German aircraft returned to their bases. What had begun as parity had become annihilation by arithmetic. For the Luftwaffe, the warning signs had appeared months earlier. Pilots wrote of fuel shortages, spare part delays, and training hours reduced from 200 to barely 30. New recruits went to war, having fired their guns only once. Mechanics worked in half-bombed hangars, stripping wrecks for usable parts. Radar stations reported incoming raids they no longer had planes to intercept. Against this shrinking air force came a storm of metal and industry. The P-47 Thunderbolt, the P-51 Mustang, and the B-17 Flying Fortress filled the upper atmosphere in endless formations, above 25,000 feet, where oxygen thinned and engines gasped. The American fighters still roared with full power. their turbo superchargers screaming like sirens of inevitability. On February 20th, 1944, the Allies launched Operation Argument, what pilots called Big Week. For 6 days, thousands of bombers and escorting P-47s and P-51s struck at every major aircraft factory in Germany. In that single week, the Luftwaffe lost nearly 400 fighters and 100 veteran pilots, men who could never be replaced. The factories they died defending were left smoking ruins. From that moment, the German Air Force ceased to exist as a coherent weapon. It fought bravely, but no longer effectively. Every replacement aircraft was destroyed faster than it could be built. Every pilot trained was killed before training mattered. The industrial war that Werner Schultz had foreseen was no longer theoretical. It was visible in contrails that stretched unopposed across the German sky. The statistics were merciless. In 1943, Germany produced about 25,000 aircraft. In 1944, the United States produced nearly 100,000. By late 1944, the average Luftwaffe fighter unit fielded just 8 serviceable planes out of 40 on paper. Fuel became the final enemy. Allied bombing of synthetic fuel plants at Luna and Plitz turned every drop of aviation gasoline into gold. Squadrons were grounded for lack of kerosene. Jets like the Me-262, technological marvels decades ahead of their time, sat motionless on runways because there was nothing to put in their tanks. Meanwhile, the Thunderbolt ruled the medium altitudes. Over France, Belgium, and the Ruhr, P-47s hunted trains, convoys, and airfields. Their 8 50 caliber guns shredded locomotives and flak batteries alike. Villagers learned to dive for cover at the sound of a distant metallic growl. In reports from the German Army High Command, a new phrase appeared repeatedly: movement by day impossible. By mid-1944, German infantry advancing by daylight risked instant annihilation. Supply convoys moved only at night, headlights covered, fuel trucks hidden under trees. Yet even darkness offered no safety. Radar-guided intruders and long-range night fighters brought the war into the black sky. Inside the Luftwaffe command, despair replaced strategy. Meetings in Berlin grew quiet. Arguments gave way to silence. When Albert Speer presented production figures to Hitler in late 1944, the numbers revealed a system devouring itself. Factories relocated underground, workers starving, output collapsing. Hitler demanded new wonder weapons. Engineers like Schultz knew the truth. There was no more industry to build them. Pilots who had once dominated Europe now measured success by survival. Aces with 30 victories were shot down by teenagers flying Thunderbolts in overwhelming numbers. The ratio of kills inverted. Where once a German might destroy 5 Allied planes before dying, now 5 Germans fell for each Thunderbolt lost. For the men in the air, defeat did not come as a moment. It came as exhaustion. Each mission felt heavier, each takeoff slower, each sky more crowded with contrails they could not reach. The Luftwaffe was dying not of combat, but of starvation, of fuel, of metal, of time. By the spring of 1945, Allied bombers roamed at will over the Reich. Cities burned in daylight. Bridges vanished overnight. When the Red Army crossed the Oder and the Americans reached the Rhine, almost no German aircraft rose to challenge them. The once mighty Luftwaffe had become a ghost. On May 8, 1945, the war ended. In American occupation zones, captured engineers were shown photographs of their former adversary assembly lines in Detroit and Long Island, turning out aircraft engines by the tens of thousands. One of them, possibly Schultz himself, looked at the pictures and said quietly, "Now we understand. We were fighting a nation, not an army." The statement became the epitaph of the air war. The Thunderbolt, that heavy, inelegant, unstoppable machine, had not only won battles, it had proved the truth that still defines modern warfare, that the sky belongs not to the bravest, but to the most prepared. When the guns finally fell silent in 1945, the world that emerged was one reshaped by engines. From the ashes of Europe rose a single truth: wars were no longer won by generals alone. They were won by production lines, by logistics, by the invisible hands that built the machines carrying the fight across oceans and skies. The P-47 Thunderbolt, once mocked for its weight and size, had become a legend. More than 15,600 were built, more than any other American fighter of the war. It flew over every front, from the burning forests of Normandy to the jungles of Burma, from the frozen skies above the Ardennes to the last days of Japan. Its record spoke for itself. The Thunderbolt destroyed over 7,000 enemy aircraft, 86,000 ground vehicles, and 9,000 locomotives. But numbers alone could not define its legacy. What the P-47 represented was a philosophy, a new way of waging war. Unlike the sleek, handcrafted machines of pre-war Europe, the Thunderbolt was a product of scale, not elegance. It embodied the transition from craftsmanship to system, from the artist's hand to the factory's rhythm. It was proof that the age of individual genius had yielded to the age of industrial genius. In post-war Germany, engineers studying the wreckage of the Luftwaffe admitted the same truth that had haunted Werner Schultz 2 years earlier. We were defeated before the first dogfight. We just didn't know it yet. That realization marked the end of one era and the beginning of another. The jet age that followed the Me-262, the F-86 Sabre, the MiG-15, all inherited lessons from the Thunderbolt. Its airframe design influenced post-war fighters for decades, its radial engine technology refined into civilian transport, and its philosophy, mass production as power, became the blueprint for modern air strategy. But perhaps the most profound legacy was psychological. The P-47 proved that freedom, when organized and industrialized, could outmatch tyranny powered by ideology. It showed that democracy, for all its inefficiency and debate, could build faster, adapt quicker, and recover stronger than any dictatorship. Every rivet in its aluminum skin was a statement of that resilience. To its pilots, it was more than a machine. They called it the Jug, short for Juggernaut. Heavy, indestructible, protective. It brought thousands of young men home when lighter aircraft would have failed. Pilots spoke of limping back with holes in the wings, engines sputtering, controls frozen, and still landing safely. One pilot said, "You could shoot a P-47 to pieces, and it would fly you home out of sheer loyalty." In the years after the war, Thunderbolts were sold or scrapped, replaced by faster, sleeker jets. But in the memories of those who built and flew them, the Jug never faded. It represented not just victory, but survival, the triumph of endurance over fragility. In museums today, its immense frame still commands awe. Visitors walk beneath its wings and see more than a fighter. They see the echo of an age when nations turned their factories into fortresses and their engineers into soldiers. When mathematics replaced myth, when industry became destiny. For the German engineers, who once examined it in disbelief, the Thunderbolt had been a revelation of defeat. For the Americans who built it, it became a symbol of unity, proof that a country of workers, farmers, and dreamers could produce a weapon so vast, so reliable, that no empire could stand against it. And for history itself, the P-47 stands as a monument to the industrial age of warfare, to the moment humanity learned that courage alone could no longer win wars, that steel and fuel could decide the fate of civilizations. In the end, the story of the P-47 is not just about an airplane. It is the story of a turning point when the battlefield left the trenches and took to the factories, when one man's ingenuity gave way to the power of millions, when the roar of a radio engine became the sound of modern victory. It was not beauty that won the war. It was endurance. And in the sky, endurance had a name, the Thunderbolt.